All right. Good afternoon, everybody. My name is Anders Heilsberg. I'm a technical fellow in the developer division at Microsoft, where I work on C# and TypeScript. And I'm here today to talk about TypeScript, which is a project that we have been working on for probably 2 or 3 years now. We went public with TypeScript about 18 months ago. TypeScript basically is the answer to feedback that we've gotten, in particular over the last 5 years, that writing large applications in JavaScript is hard. JavaScript, the language, was designed in 3 weeks back in the mid-90s as a quick answer to Java. Was never intended by Netscape, and was never intended for more than 100 or maybe 1,000 lines at most. And now people are, with regularity, writing 100,000 or even million-line apps in JavaScript. And it's hard to write these large apps because JavaScript doesn't have any of the concepts that we need for structuring large apps, such as classes or modules or interfaces or static typing. Indeed, the lack of static typing, I think, is in particular a hard problem. If you think about what it is that powers modern IDEs that we've all come to know and love, things like statement completion, refactoring, find all references, go to definition, et cetera, et cetera. But below all of that is knowledge produced by a compiler that reasons about static types in the program. And without any static types, it's very, very hard to provide a meaningful tooling experience, and it's almost impossible to do refactorings that are safe, and gradually these large JavaScript code bases end up sort of being read-only. You dare not touch anything once they get to a certain size, and all you could do is sort of hack around what's already there. So as we thought about where to go with JavaScript tooling a few years back, we thought, wouldn't it be great if we could strengthen JavaScript with these things that are missing, like classes, modules, optional static typing, but do so in a manner that doesn't actually compromise the key value proposition of JavaScript, which is it runs everywhere on any browser, any host, any OS. And the answer to that is TypeScript. So TypeScript is, well, markety speak, a language for large-scale application JavaScript development. Technically, TypeScript is a typed superset of JavaScript that compiles back to plain JavaScript. And TypeScript is written in itself and therefore compiles to JavaScript, and that JavaScript runs in any browser, on any host, on any OS. And the entire project is open source and hosted on Codeplex. So TypeScript starts with JavaScript. In fact, any piece of JavaScript is valid TypeScript. You can copy and paste JavaScript code into a TypeScript file, and TypeScript works with all of the existing JavaScript frameworks, and that is just super important because there are so many of them out there. And new ones coming every day, right? I mean, Underscore, Backbone, Knockout, Angular, you name it. And TypeScript works with all of them and can work even better if you provide static types for them, and we'll see how that all hangs together. So what TypeScript then adds on top of JavaScript is optional static typing, classes, modules, interfaces. And then on top of that foundation, we've built a great tooling experience, compiler, language service, integrated into Visual Studio, but also available, fully open source to integrate into all sorts of other IDEs. And there are today plugins for Eclipse and JetBrains and VI and Sublime Text and you name it. But when the compiler compiles TypeScript, the code just goes back to just plain old JavaScript. In fact, I would say it goes back to idiomatic JavaScript, the JavaScript that you yourself would have had to write if you wanted to use classes or modules in your JavaScript code. So today, I am pleased to announce the, thank you. the release of TypeScript 1.0. TypeScript is now an officially supported language in Visual Studio. Subsequent versions of Visual Studio will have TypeScript in them, just like it has C# and Visual Basic. But we are still fully committed to the open source way of doing things, so everything that we release in VS will also be released open source. So let's try to take a look at TypeScript. I'm going to switch to my demo machine here, and then let's play with the product. So what I have here is Visual Studio 2013 with TypeScript in it. And I'm just going to start writing some code here. I'm going to start with a little JavaScript function that sorts an array by name. Because TypeScript is just JavaScript, I can just grab JavaScript and put it into my TypeScript file. Now, but because there are no type annotations in this code, we don't really know a lot about what this code does. You'll see if I hover over this argument A here, it just tells me that, well, A could be of any type, and therefore, the result could be anything, and therefore sort by name could return anything. And if I try to get statement completion, we can't give you anything because we don't know anything yet. Now, so somehow we need to get static types into this JavaScript here so the IDE can reason about things. And we're not the first to get this great idea. Google has a tool set called Google Closure, for example, where you can add type annotations in comments. It looks sort of like that up there on the screen. And that kind of works. But as I've said before, I don't think Commons is the best place to host a type system. It's not particularly expressive. It's also not particularly pretty to look at. So what we allow you to do instead is to simply write type annotations in your code. And so here, for example, we know that this A is going to be an array. We may not know an array of what, but we could say that we wanted the compiler to treat it as an array of anything. And once we do that, stuff starts to light up already. First of all, you can see now that from that, we can infer that result must then be an array of anything, and since our function returns result, then sort by name must be a function that takes any array and returns any array. Also, now that we've said something about A, if I type A dot, we can show you statement completion here because we know what all of the methods of array are, and we know that we're dealing with an array. So all of a sudden, the authoring experience becomes a lot easier and a lot less error-prone. Now, when I compile this code, and you'll see that later too, these type annotations that I'm adding just disappear. So they're really only there for development time purposes. They're really just hints to the system or the IDE how to treat these types, but they go away at runtime. And you're just left with plain JavaScript. Okay, so you can see from this function here that we're obviously, we're first copying the array using the slice function, and then we're calling the built-in sort method on an array, and that sort function then in turn takes a callback where we're supposed to compare two elements here, x and y. But since we haven't told the service here about what the types of x and y are, they just come in as type any. But we can sort of see here that, well, we're obviously sorting them by their name property. So maybe we could say something more about what we're doing here. We could, for example, declare an interface, call it entity, that has a property name of type string. And then we could say that A is an array of entities, like so. And now a couple of things happen. First of all, we now know what the types of x and y are. So we can actually infer by flowing the types, that when you call slice on an array of entities, you get another array of entities. When you call sort on that, then your callback function is going to be given two entities. So we can infer that the types of x and y are entity, which in turn means that we know that they have a name property. So if I press dot in here, we can show you statement completion and show you the name property and so forth. Now, you'll also note that something else happened here. All of a sudden, we get some red squigglies on this local compare. Now, it turns out that there was a bug in my app here, but because JavaScript is a dynamic language, you don't find out about these things until the space shuttle flies, so to speak. But it sure is nice to know it on beforehand, and with static typing, we actually can know these things. So if I try to type the same code that we have there, x.name. You'll see that there's a method on string called locale compare, not local compare, and that was clearly the one I meant to use, so I can correct it like that, and the error goes away. But that, again, is one of the examples of what static typing can do for you. Now, another thing that static typing can do is it can know all about the different identifiers that occur in your program. Let's just say I have another name here, a local variable name. So now I have two things in my program called name. I have a local variable, and I have a property. Now, if I were to refactor this as JavaScript, and now just pretend that I have like 50,000 lines with lots of name identifiers, and I want to change the name of the name property to, say, entity name, but I don't want to mess with the local variables. What am I going to do? I need to manually sit there and look at every occurrence of these identifiers, and no one dares do that, right? It just becomes read-only. Now, here, though, I can actually have the IDE help me refactor. I can bring up the refactor rename, and then call this guy entity name, for example. And you'll see that we rename the property in the declaration and the use, but not the local variable, because through static typing, we can tell the difference between these two. And this is how you get safe refactorings in this code. So this entity guy I wrote here is basically just a description. An interface in TypeScript is it's just, in a sense, something that says that an entity is an object that has a name property. And anything that has a name property appears to implement the interface. You don't have to explicitly implement interfaces. Rather, TypeScript uses what's known as structural typing, where if it walks like a duck and quacks like a duck, it is a duck. Duck typing is what some people like to call it too. Now, I could, on my entity here, for example, say more things about it. Say, for example, that an entity is a thing that has a name and a price. And then let's try to create an entity. I could declare a variable of type entity, like so. And then now if I say e dot, you'll see that we know there's a name of type string and a price of type number. I could also try to write it as an object literal, and in here we can now offer up help that name has to be a string. Let's call that a hammer here. And price, say, $5.95, for example, like so. And because and here what you saw actually was a phenomenon we call contextual typing, where if we know that you're assigning an object literal to a variable whose type is known, then we can flow the type the other way into the object literal and contextually type whatever goes on in there, because we know what the final result is supposed to be. Let's say I were to add another, well, I'll call it, say, this, like in stock, whoops, colon Boolean here, for example, property to my entity. Well, now I get an error saying, and we can actually tell you what's the matter here, is you're missing the in stock property that you're supposed to have. So I could either then go add an in stock property, but I could also say that entities can optionally have an in stock property. And I use a question mark modifier to indicate that. And that means if you give an in stock property in an instance of this type, then it must be of type Boolean in order to satisfy the contract. And now if I, down here, whoops, add an in stock, and I say true, then things are happy. But if I say, oh, I've got 10 in stock, then whoops, again, I get an error because the types are incompatible. Of course, in interfaces, you can also add methods. Let's try to get rid of this stuff here. And then let me go grab, say, a getName and a setName method. And now we're declaring that an entity is a thing that has a name and a price, and two methods, one called getName and one called setName, that we can now go implement here. So getName, let's say, here, return this dot name, and setName, function of s. Whoops, did I get that right? Let me just, oh, setName, sorry. And now if I press dot on s, you'll see that again, we have been able to flow the types contextually into this object literal. We know that you're writing an implementation of the setName method, and it's supposed to take a value of type string. And here, since I didn't give a type annotation, we can infer that the type of s must be string, and therefore we can show you all the methods of string right here. So we can just in here say this dot name equals s, for example, like so. All right. So that's sort of a brief little introduction to how types work in TypeScript. And I should say that actually in these interface declarations, you can pretty much model everything that occurs in JavaScript's dynamic type system. So you can also say something about what happens if it's a constructor function, and what happens if you index an entity, what type do you get out of there. All of the things that are pertinent to the dynamic type system in JavaScript. In fact, the way to think of TypeScript really is that it is a static formalization of JavaScript's dynamic runtime type system, because JavaScript does have a type system. It's just, it isn't manifest as such other than when the program runs. All right. Let's try to switch and, in fact, let's try to take this code here with us. I'll get rid of this stuff and this stuff here. And then let's try to grab this and switch to the TypeScript playground, which is a little place on our TypeScript website where you can type in TypeScript code and see the compiled output. So let me try to paste in the code that I just had. And in here, I am supposed to type TypeScript code, and over here we show you the output of the compiler. And you'll note that my code looks exactly the same, except the types evaporated. And that's really, in a sense, what the TypeScript compiler does, is it understands the types, it checks the types, and then it erases the types and emits just the JavaScript that you wrote. And that's actually the artifact that ends up running when you run a TypeScript program. So let's try to add some code to, in fact, go back and grab some code over here. This guy here, and let's try to paste in some more code here. Where let's get ourselves a few products, and then let's try to use our sort method. We'll call sort by name. And you'll see that we actually, in the playground here, provide statement completion based on, so I can select this guy here. And we show you what the parameters are and whatever. And this is the same language service that you saw running inside Visual Studio, but now it's actually running in the browser. Because the entire language service is written in TypeScript, it can run anywhere. It can even run on your phone, on Android device, anywhere. It doesn't matter. And here we are actually running it inside the browser. So I'll pick the sort by name of products here. And now, if I say then, you'll see that because products, first you'll see that we have inferred here the type of products to be an array of things that have a name, price, and ID property. So just from the code that you wrote, you didn't actually say any types, but we can infer the type from the structure of the code, right? And so obviously a product has a name property, and therefore product satisfies the entity contract with a name and a price. In fact, let's even just get rid of price here as well. But of course, that also means that what I get out of my sort function, because it takes an entity array and returns, we've inferred that it returns an array of entities. Now, if I then say sorted sub0 dot, you'll see that something got lost in the translation here. All I see now is a name property, even though what went in was a thing that had name and price and ID, right? In a sense, how we really want to describe our sort function is that it's a thing that takes some array of some type and returns an array of the same type. And that's where generics come to the rescue. So I could actually change the declaration of sort by name and say, it is a thing that takes an array of some type T, and then we inferred that it then returns an array of that same type T. And now, down here, if I say sorted sub0 dot, you'll see that the entities now have flowed through our sort method using generics. And in a sense, generics here in TypeScript, the purpose of the generics are really to flow types and give you sort of a higher bandwidth conduit with which you can describe the flow of static types in your program. Now, you'll also note that, that a couple of errors got highlighted here, right? Like all of a sudden it says the property name does not exist on a value of type T. And in a sense, that's true, right? Because we've said T. Well, T could be anything. It could be something that doesn't have a name property. So really, we need to constrain our type argument here, which we can do by adding a constraint. So we can say it extends entity. And now the compiler will check that whatever you pass to sort by name is a thing that as minimally is an entity, but could be more, and it will preserve the more in its result, right? Cool, thank you, thank you. All right, so now you're all going to worry, oh my God, generics in JavaScript, that's got to be insanely expensive at runtime, right? I mean, but look at the output code, right? All of these types, it's an illusion. They just evaporate. So when we compile, all you're left with is JavaScript. And really, in a sense, all you've done with the types is you have described how types flow in the application, such that the tooling can reason about them and help you validate your program, give you statement completion, but there's zero runtime overhead from this. Okay. Let me just try to just see if we can actually make this code run here. So what we'll say is, go back and grab a little piece of code here. And then let's paste it here. So what we're going to do now is we're going to take our sorted array, and then we're going to call json.stringify on it and actually show it. And now let's try to run the code and see that it works. And indeed, we see that things get sorted by their name, hammer, lawnmower, bad luck toaster. Now, let's say that we wanted to be a little more fancy in our sort function here. You know, this particular sort function can only sort things that have a name property. What if we really wanted to generalize it, like to have the ability to sort anything? Well, one way we could do that is we could rewrite it to take a callback that picks out the key of each object and then sort it by that. So let me try to actually pick a little piece of code from over here that does that, and let me try to paste it in. Like so. So now I've written my sort by method as a function that takes a generic array T that now isn't constrained, and then it takes a callback function that presents an item of type T, and you're supposed to return some property of that item, and then we're going to compare the keys that you returned us. Now, of course, down in the call here, we see that we need to pass an extra argument. So I can now actually write a little lambda expression here and say x, whoops, sort by name of, oh, sorry, it's called sort by now. It's not called sort by name. Sort by of products, comma, x, arrow. And here I'm supposed to give a callback function, and now, oh, I did not type it right. Sorry. There we go, x arrow, x dot. And now you see that we actually have flowed the type through, and so we know that the x in your callback here has type product, and now we can pick, say, first sort by name, for example, and we can try to run this here and see that, yes, that sorts by name. Thank you. But we could then change and sort by price, like so, and let's try to run that. Run, and now you see they come out sorted by price instead. Now, one thing that's interesting is I use this arrow function syntax, which doesn't actually exist in ECMAScript or JavaScript today, but it will once ECMAScript 6 gets ratified. In fact, it is already implemented in some VMs, but not all. But note what we compile it to. We actually compile it to an inline function, which is really how it's defined. And there are also some definitions about how this works in an arrow function that we do. But so the thing that's cool about this is, in a sense, that TypeScript gives you a preview of ECMAScript 6 today, but we can compile it to code that can run on an ECMAScript 3 browser. And we can do that with several of the features. Indeed, our syntax for classes, as you'll see shortly here, is very inspired or very closely aligned with ECMAScript 6. And in a sense, you can think of TypeScript as a preview of ECMAScript 6 with a down-level story and static typing on top. OK, let me try to go back and just show one thing over here again in Visual Studio. So you saw that we sort of knew, for example, that an array has a slice method. And we actually know something about its arguments, like start and end, and we even know a comment here that says it returns a section of an array. Now you're going to wonder, well, where did this information come from? Well, we can actually ask to go to the definition of the slice method, and that jumps us into a file called lib.d.ts. This extension .d.ts is an extension, or is a declaration file. It's a file that contains nothing but type declarations. There's no code in it, actually. You can sort of think of it as a TypeScript header file, if you will. This particular file tells you all about the entire JavaScript runtime library and the DOM. It's about 15,000 lines of code, if you look, and comments. If we go to the end here, what do we have? You have 14,900 lines of code. And in here, we have the entire JavaScript DOM runtime library described with full precision. Now, these are the 15,000 lines of type declaration that you're supposed to remember by heart when you're writing JavaScript code, right? Because, hey, man, it's cool, it's dynamic, it's like, I know these things. But, of course, we don't know these things. At least we don't know them without first looking them up, and it takes time. And that's exactly what computers are supposed to do for you, right? They're supposed to help you show this. And by writing these declaration files, it's possible for us to gradually type things. And you'll note that this declaration file disappears again. There's no cost to having it there. But once you have it, you actually get a much better tooling experience. Now, the other cool thing is that it's not just us who can write these declaration files. Anyone can write these declaration files. And you can write them for any JavaScript framework. And then when you include these declaration files, you get a better experience. Indeed, one of the fantastic things that happened shortly after we released the first previews of TypeScript was a site sprung up on GitHub called Definitely Typed. And it's really a repository for TypeScript declaration files that some guy in Russia started, and then some other guys jumped in. And now there's a very active community, about 400 different committers on Definitely Typed, that has produced about, I think, 380 is the last number that I saw. 380 distinct frameworks now have static typing for them that are being maintained completely organically on an open source site called Definitely Typed. And it's a fantastic resource because now You know, there's coverage for 90% of all the top JavaScript frameworks, so it's probably higher than 90% at this point. So if you want to use Angular, jQuery, underscore, you name it, they're all there. You just pick them up. And we can even provision them using NuGet, and that's one of the things that you'll see later in the demo here, that we actually have NuGet. There's someone else built a thing that scrapes definitely typed and produces NuGet packages from each of the declaration files, and now you can just automatically get those and simply provision your projects super easily to get the right declaration files. Okay, let's go back and try to look a little bit at how you write classes and interfaces in here. I'm going to try to write a class called point and declare two properties in my class, x:number and y:number. There. And over here, you'll see what we do when you write a class, what we compile it into. This is actually sort of idiomatic JavaScript that puts everything in a function closure to give privacy. And then it declares a constructor function called point that it just returns. Now, with that in hand, I can now create myself a varp equals new point. And I can now say p.x equals 10, p.y equals 20, for example. And you'll see the generated code over here. Now, I might actually want to like maybe pass my x and y to the constructor a point, but now the IDE complains here and tells me, well, we don't have the constructor function doesn't take arguments, so we're going to need to write a constructor then, and we could do that. So we can say constructor of x:number, y:number. There we go, and then we can say this dot x equals x and this dot y equals y. And you'll see that in the generated code, we now put properties on the instance that the constructor function is initializing. Now, this particular syntax is closely aligned with ECMAScript 6. This is exactly what classes are going to look like in ECMAScript 6 once browsers have native support for classes. And of course, once ECMAScript 6 comes out, we can have a compilation mode for TypeScript that says, please produce ES6 output, and then we can just emit it as a class again. But you can also emit down level if you want to. Now, of course, the one thing that is still going to set TypeScript apart is the static typing. There are no plans in ECMAScript to do static typing, and static typing really is the thing that powers it all underneath. So TypeScript will still remain just as relevant as it is today when ECMAScript 6 comes out. We can, of course, write methods here also. We can write a distance method that returns the length of the vector given by the point. So here we'll say return math.square root, and here you see statement completion on the square root method, and we'll take this dot x times this dot x plus this dot y times this dot y, say, like so. I'll keep that up there. Okay, and now, if I say p dot, you'll see that there's a dist method that returns number, and we know, again, you know, all how the types are flowing here. We also support static, so I can have static property, static origin equals new point of 0, 0, for example. And if you look into generated code now, it's starting to get a little more involved, right? This is why classes are hard in JavaScript without a helper library, and this is why all of the frameworks out there have different sort of helper methods you can call to construct your classes. But you'll see that we put instance variables on the instance. We put methods on the prototype object of the constructor function, and we put statics on as properties on the constructor function. And these are sort of the established ways you're supposed to do this in JavaScript, but it sure is nice to have, you know, a compiler do it for you. We also support public and private annotation, so you could say private color, :string here, for example. And then down here, we could say this dot color equals red. Now, and you'll note that in here we get statement completion, but outside of the class, there is no color member. And so private basically means restrict access to this member to only be within the class where it's declared. However, if you look at the emitted code, you go, well, what do you mean? It's not private. I could just say, well, yeah. There are no private fields in JavaScript. But that doesn't mean that it's not useful to have a compiler check for you that you yourself never do this anywhere in your code, right? Of course, also, as ECMAScript 6 comes out, one of the things that they're going to support in ECMAScript 6 is a thing called symbols, which is the ability to have properties with hidden names. And we could technically compile private members into that, and we may do that in a future release. Another thing we support is this pattern of writing property declarations, taking them as parameters to the constructor, and then initializing them in the constructor is actually a very common pattern. So one thing we support is that you can just put an annotation on the constructor parameters saying, please make these into public properties. And then that will automatically declare a property by the same name as the constructor argument and inject code into the constructor that initializes the property. We also support an ECMAScript 6 feature, which is default argument value. So I can say the default argument value here is 0, and for x is 0 also. And you'll note that we then emit a little statement that initializes the parameter if it was undefined. And also now, of course, the type checker knows that there are default properties or default parameter values, so I don't have to give arguments now, and they will just default to 0. Okay, so that's sort of briefly what it looks like to write a class. We could also, of course, we support inheritance. Let's try to write a class that inherits from point, so we'll write a point3d, extends point, like so. And then in here, we will add a constructor that takes x colon number, comma y colon number. And then we'll add a z property. And then in here, we're going to call super of x comma y. OK, so let's pause here and look at what got emitted for that. Now you'll see that the code generation starts to get a little more involved when you're dealing with inheritance. But we basically, again, generate a function closure, and then we pass in the base class as an argument to this function closure, and then call it underbar super inside the function closure. Then we have a constructor function point3d, and in here we call underbar super, the super constructor. And then we have a helper here called underbar extends that gets emitted at the beginning of the source file. This is the only time TypeScript emits code that you didn't write. And it's only 4 lines of code, and we only emit it if you have a derived class in this particular source file. And it's just a helper that helps set up the prototype chain and copies all of the static properties from one constructor object to the other. And of course, in here, we can override methods and call super on them and so forth. Another thing TypeScript adds that JavaScript is missing is modules. I could try to put my, let's say I had my var p equals new point here, 10, 20, say. I could put point inside a module. Let's say I have a whole bunch of classes, and my global scope is kind of getting polluted. I could enclose all of this in a module. So I could say module utils, like so. Like that. There. And then you see what happens in the generated code is that we now put everything inside a function closure again. And now I can export members out of this module, and you'll see that makes them properties on the object, on the module object. And now we've effectively namespaced. So if I say utils dot, there's now a utils dot point. And you can do this, and this is basically, in a sense, giving JavaScript namespaces and the ability to encapsulate code. It's a very common pattern that almost all of the frameworks use, like jQuery, for example, defines one object called $, and everything sits inside that function closure, and everything gets exposed as properties off of that. And we basically give it language support and type checking support as well. We call these kinds of modules internal modules. There's another kind of modules in JavaScript that are very popular currently, and those are called, we call them external modules. They're the kinds of modules that Node.js uses or Require.js with the asynchronous module definition. I'm going to try to switch and show you a little bit about what it looks like to use those. In fact, what I'm going to do is show you here, so what we've looked at here was well, it was just sort of code that could run on any tier. Of course, TypeScript is super relevant when you're writing code that runs in a browser. But TypeScript works equally well with JavaScript on the server. A very popular server-side framework is Node.js. And Node.js has an interesting module system that aligns with a specification called CommonJS. And I'll show you what it looks like to use TypeScript with Node. In fact, I'm going to build a little app that has 2 modules in it. So I will first open a blank file called server.ts here. Demo node server.ts here. Here's a blank file. The first thing I'm going to do in this file here is I am going to reference node.d.ts. And by referencing the node declaration file, I now get static types for all of the stuff that Node supports. So right out of the gate, I can now actually get statement completion on stuff in Node. So what I want to export here is I want to export a function create server that takes a port type number and a message type string. Wow, these alerts just keep on coming. Jeez, okay. All right, so in here then, I can now start using stuff from Node. Oh, so first I actually need to say import HTTP equals require of HTTP and import the HTTP module from Node. Did I not do that right? Here, let me just see if I have a snippet for it instead here. There. What is it telling me here? Module cannot be aliased to a non-module type. I'm not sure what's going on here. I am stumped momentarily. Let me just try this again here. So open server.ts, and let's just grab the code here instead. Okay, here's the code that I wanted to write. Oh, I am not sure what's going on here. What's that? Oh. I said what? Oh, require, of course. Oh, and now I have to set the module flag. Yes, okay. All right, I don't actually have to do that right now since I'm going to compile it with the command line compiler. But so anyway, in here now, I can say HTTP dot, and you see that I get statement completion on Node's modules like create server. And in here, we know that create server in Node is going to pass a request and a response object, so I can add those and write my code. And so here, you see it already written. So anyway, that's, and then finally, I start that little Node server by listening on port. And again, as I'm writing this code, you'll see that when I say listen here, we get statement completion. We can take the port argument and so forth. Okay. Now this error here simply reminds me that I need to compile with the module flag if I'm using CommonJS modules. I can also set up my project options to do that. But that's basically my little server. Let me now try to create a little client of this server. And in here, I'm going to say import server equals require of /server, like so. And that basically imports now the module that I just wrote over there. And now I can say server dot, and you'll see that I get statement completion on the server that I just wrote. Okay. And in here, I can now pass it 1337, comma, say hello build. And then we can just say console.log of listening on 1337, like so. There. So that's my little app. Let me switch and just for fun use the command line compiler to compile it. You'll see that, that in here I now have my 3 files. And I can simply just tell the command line compiler to compile hello.ts with the module CommonJS switch on it. And if we look now, what resulted from that is 2 JavaScript files. And if I type those, you'll see that basically here's the code that I wrote. Whoops, if I type the JS file, you'll see that it's the same file, just with the types removed, right? And if I type hello.js, you'll see that here's my little hello, again, with type annotations removed. Now to start that, I just say node hello, like so. And I can now go to the browser, go to whack localhost. Oh, I've been there before, and there we go, hello build. So that's, thank you. That's Node with TypeScript. Okay. Next thing I wanted to show is what it looks like to convert an existing JavaScript project to use TypeScript, which is something that we find that a lot of people do because they already have some code and they want to use TypeScript with their existing JavaScript project. Now, to do that, I'm going to try to open up an existing project here called AudioScope. And we'll just open up AudioScope solution. There we go. Can pin this maybe here. Okay, so this is just a little app. In fact, let's just try to run it, and you'll see what it does. It's a little file that allows me to inspect WAV files and see them graphically. Okay. Now, this thing has three JavaScript files in it, of course, with no type annotations, whatever. Now, as I said earlier, one way to get started with TypeScript is to simply rename your files or copy and paste them into a TypeScript file. But I'm just going to start by renaming them here. So we'll just do rename, and we'll just simply call these guys .ts instead. Now, as I do that, it says, oh, are you sure? Yes, I'm sure I want to do that. Then it says, I'm noticing that you're adding a TypeScript file to your project. Would you like to configure it and actually use NuGet to get libraries, for example, that you might be using in here with the static type information that they can provide? And then we go look at, see if the internet is working for us here. It doesn't matter. We don't need it here, so we can just not wait for that. Let's rename this guy also to .ts. And let's rename the last file to .ts. There. Great. Now, of course, as I did this, let me just try to close these files here again. And let's look at what has happened as a result of that. If I look in my files here now, you'll see that we get some errors because now TypeScript is starting to infer things about your code, and certain things it can infer, but certain other things it can't. For example, here we're saying document by .get element by ID of a wave view. That causes us to infer that C is of type HTML element. but then it's using a property that doesn't exist on all HTML elements. It only exists on some of them. And TypeScript is conservative here and tells you there's a warning. Now, we'll look at how to address that. But first, note that I can actually still run the code. So if I say Control F5 here, I'll get some errors in the output, but it still produces output, and it still works. So the errors, in a sense, are just diagnostics. Even in the face of errors, as long as they're not parse errors, we can still emit code and allow you to run the code. But let's try to get rid of these errors here. So basically, what's going on here is if we look at default.htm, we can see that there are two objects in here. We have a wave viewer, which is a canvas, and we have a selector here of type select. So let's try to first go to app here where we create the file selector, and let's instead then tell TypeScript that this thing is of an HTML select element, and then you see that the errors go away. What I added here, that's a type assertion. I'm basically asserting that, trust me, this thing is actually an HTML select element. And then the type checker will check according to that instead. It's really sort of like a typecast, right? The other one here, it's the same. We basically just need to tell it that what we have here is an HTML canvas element. And then you'll see that all of our errors disappear. Well, except for one error down here. And this is kind of interesting. All of a sudden, the type checker now has enough information that it can point out that there's a local variable you're using here that isn't declared. And I don't know if you can all see what the problem is here, but it's actually that someone misspelled this local, put an E here instead of an O. Now, these are the kinds of things that, oh, I could have sworn I had unit tests for it and whatever, and basically this error only shows up if you have 8 bits per sample in your WAV file, but I guess we didn't, right? And so we never found it. Well, it turns out if I try to run with this error in place, and I click here, I carefully avoided clicking on notify.wave because it is, in fact, an 8-bit WAV file. But unless you have all of these unit tests in place, and we find time after time when people convert their JavaScript projects that they discover things that they could have sworn they had a unit test for, but they didn't. And the type checker starts all of a sudden pointing out stuff that they thought was like perfect. Great. So we can fix our bug here and call it scale factor instead. Now, of course, still with this code here, most of my variables and parameters in here are just typed as any, like WAV file is just anything, right? And ideally, really, we kind of want to go through and now start adding types to everything. And in fact, one way we can do that is we can tell the type checker by going to Properties, TypeScript Build, and then we can say, don't allow implicit any types. And what we're telling the type checker here is, you must put annotations on everything. We will never allow you not to have an annotation. Because when you don't have an annotation, we don't know stuff, and then things could go wrong, right? So this is, in a sense, a stricter mode of checking. And now, all of a sudden, you see errors, more errors pop up, and now we can go stamp those out. The way we would do that here, for example, is we would change first this guy here. Really, we wanted this to be an enum. So we can change that to be an enum. This was a constructor function that we could have actually written as a class. Here, we could add type annotations to these two functions on their parameters and then stamp out those errors. And then finally, on load file here, we could add type annotations to that. And now the errors go away gradually. Now, of course, there's still an error over here, but we really know that we wanted this guy to be a WAV file, so we can add that annotation as well. And down here, scale point, well, that really was supposed to be a number. And now all the errors are gone, and now we actually know that we have, well, there's still our scale. Oh, yeah, that's hidden from the last build. Now we know, with a much higher degree of certainty, that all of the types have been checked. And in fact, now we can safely start refactoring stuff in this code. So I can now go back here, and let's say, for example, I wanted to change my data property to be called wave data. So I can now pick refactor rename. and then rename this to wave data. And now look, if we undo, redo, well, let's see, can we see it in here? Here we go. No. Anyway, let me try that again. Refactor, rename, wave data, we'll call it, okay. And then let's go down and let's just redo, undo, and see the places where this had an effect. You see here that data got renamed to wave data, and it actually, thank you. And that actually also happened over in this file over here. You see data became wave data. So that's just sort of an idea. It gives you an idea of what it feels like to start with JavaScript and then gradually type it and then gradually get the benefits of static typing. But the interesting thing here is that nothing forces you to type strongly everything. And it's been a very interesting project, just from a purely academic point of view to work on. Traditionally, type systems were very much an on-off switch. Either you were in a purely dynamic language where you knew nothing about the type statically, or you were in a strictly enforced statically typed language where you had to know every type of everything. But we've, in a sense, with TypeScript, turned it into a dial. And you can put the dial wherever you want it to be. You can start just with JavaScript and know very little, but then the more you dial it up, the more bennies we can give you, so to speak. Okay. I'm running low on time here. I'm going to go back to my slides and try to sum up a bit of what we've seen here. So we talked about the TypeScript type system. I think you noticed actually that in practice very few type annotations are necessary. It turns out that you typically have to put them on parameters and you have to put them on variables that don't have an initial value. But other than that, we can infer almost everything just from flowing the types through your program. You saw how generics increase the accuracy of the type system. You saw how we work with existing JavaScript libraries like Node, jQuery, et cetera. And also, you saw how really the primary purpose of types in TypeScript is to enable tooling. It's in a sense not to give hard guarantees, but it's to enable you to be much more productive and have a much better assurance that your program will work when you actually run it. We looked at classes, interfaces, modules, and basically these are the building blocks that allow our tooling to be great. They are aligned with the emerging standards like ECMAScript 6 classes and TypeScript classes are pretty much the same, and we currently support the existing module systems that are out there in the world. So since we first released TypeScript about 1.5 years ago, we've seen a tremendously strong community build around this project. We now have, by last count, 170 forks off of our repository, 500 feature requests. Well, people obviously want a lot of features, and we're hard at work at delivering them. Lots of questions on Stack Overflow, and I'm happy to announce that now that we've reached 1.0, we are actually going to start taking contributions and pull requests in the TypeScript project. Thank you. Also, in terms of support for frameworks, it's just, I can't say enough good things about this resource called Definitely Type that has organically grown out of the open source community and is now up to more than 350 frameworks have strong typings. In a sense, the community is using TypeScript to write down the metadata of programs on the web. And no one has ever done that. There's all these frameworks out there, but no one's ever actually written down how they work and how they relate to each other. And TypeScript is finally, an answer for that problem. We've got lots of tools supporting TypeScript. Because we built the compiler and the language service as open source tooling, it's possible for third parties to implement plugins to their development tools. And we've seen that now from companies, several Eclipse plugins, IntelliJ's ReSharper has TypeScript support, Sublime Text, brackets, etc. Lots of support in different build systems and so forth. Finally, TypeScript 1.0 is available now. It's in box for Visual Studio 2013. We have a plugin for 2012. We have a Node.js package, and all the code is available on Codeplex. Next on the roadmap is ECMAScript 6, which is targeted for release at the end of this year with a whole bunch of features in it. And TypeScript 2.0 is, in a sense, about chasing ECMAScript 6. And we're hard at work at that already, implementing all of those features that ECMAScript will have. And then, of course, we have additional features that we would love to do if we can find time, like asynchronous functions, like async await that we have in C#, which could be super useful in JavaScript as well. So that's a quick rundown of what's going on with the TypeScript project. I hope you guys have tried it. If not, please do. Give us your feedback and whatever. Contribute, fix a bug, and submit it, and we'd much appreciate it. So thank you very much, and I'll take some questions up here afterwards, all right? Thank you.